Okay, guys. So let's start. So we covered all these parts. Okay, and now we are here. Okay, so we will start with the spatial domain image restoration, and then we go towards the transform domain of. Okay, so these are the contents for this slide. Let's just recall what we did. First, we start with the image acquisition. Okay, and we said that we have a sampling and quantization. So this you cannot store it. There's some limitations. So we did the sampling and then quantized it. Okay, and then we did some intensity transformation, which includes these topics, which are especially histogram equalization, and then point-to-point process, which is the inversion or log transform, gamma correction. These are all the topics that we covered in the for the point transformation. Okay, then we have special filtering. We use especially smoothing and sharpening. All these filters depends on convolution. If the filter is a linear filter, if it is not linear filter, then it's not a convolution. Okay, then we move towards the frequency filtering. We discussed Fourier transform and how much sampling is required, definitely the aliasing, and then we discuss the low pass, high pass, all these filters. Okay, so now we will move forward and we just see the broader picture. Okay, so up till now, what we were doing was to see from the operation point of view how to design a filter and how to apply the filter on this. But we did not see from the image side of the picture from the image side. From the image side, we did not see that how image is looking at the filter. Then we were looking from the filter side, not from the image side. So what do you mean by this? Let's say that from the image side, we have to see that what type of distortions or the noises have been added to the image, so I can decide which filter I have to apply. So most of these things we already covered. So this will be a kind of easy with some advanced filters. Okay. So if I see the whole process of image processing, the image can have degradation, which is kind of a filter that has been applied to image, and then it can be noise that is added to image, or it can be both degradation plus noise. It's a kind of a filter that we are applying on the image, but that filter is not designed by us, but it's from the transmission or from the environment, or like if I record my speech, I have another channel, just interference, right? So this type of things appears while transmission or while taking the acquisition. Taking some pictures that are not, I will say, clear enough. Okay. So this is the whole. Yes, like a dust. Something like a dust. The good example, we did it like a dust. Dust. It can be fog. It can be snow. It can be rain. These are the things we can encounter in our image. So this is the whole model. So we have image convolved with some distortions, degradation, and then added the noise. So an image can have one of them or can both of them. Okay. And based on that, what type of operation I will required to restore the image. Okay. So what are the sources of these distortions or noise? Okay, so let's in this set of slides we are mostly concerned with only noise. We assume that there's no distortion. Okay, if you have distortion, then this again it will be told this in the next set of slides that if you have distortion, what will happen? How to recover it? So here we'll make our life a bit simple, saying that we have a noise added with we have a single image added with the noise, and we have to find what type of filter I need to recover the image itself. Okay.
With the image convolved with Poisson. So I think.
Yeah, there are two types of things. Either here addition. Noise is always addition. Okay. The convolution we call it degradation. That is separate story. That we don't call it noise.
But we think that this low pass filter convolved with this degradation, right?
Low pass filter is not a noise. Our design.
Yes, this is what we want to restore. Our need to somehow deconvolve restore.
Yeah, but
so we need with this degradation.
Yeah, yes. Okay. But the filter is convolved. The noise itself that was present was addition.
So for example, always just images.
Yes,
the distortion here is like low pass filter.
Yes.
I need to figure out.
In that case, it's a convolution. That the bloodness is a convolution. We have to find something inverse to degrade. It's addition. Noise is always addition. If it is, there are some other noise like multiplication, this, but that is very rare.
Okay. We cannot solve it by convolution.
Yes. We have to subtract it. If I know exact what the noise is, then we can. But we cannot because I don't know. Okay. So I need to design a filter that is convolution to solve this additive noise problem. Okay. So the noise comes from the lens. Let's say that we have a lens that is not working good, okay, or maybe not focused. Can be camera electronics. Okay, inside there's something light variations. Let's say dark or there's some shadow or something. Surface reflective from. Okay. Similarly, you can have digitization. You are basically using quantization, but the quantization is not on the mark. It does not define all the levels. So once you recover it, you find something missing. Similarly, in CCD cameras, light levels and sensor temperatures are the major factors to the amount of noise, and also the quality of the sensing elements. Like in the camera, it's sensing elements. It's not like no quality. You will see there's noise. Also during the transmission, when the images are transmitted, let's say wirelessly, so they're transmitted in terms of the bits. So let's say some bits are flipped up, or there's something happened. So when you restore it, there will be some distortion noise for it. Okay. So similarly, wireless transmissions, let's say you have a lightning or atmospheric disturbance that causes noise. Okay. So first we will just stick with this noise. We say that image added to a noise. Now the question is, what is noise and what is the type of filter that we use to reduce that noise? Okay. So first we will study the type of noises, and based on that type of noises, I will discuss the filters. And some of the filters we already discussed. There will be some few more filters. Okay. So generally I can say that okay, I have some distortion. It's like a filter that has been applied already, but I did not apply it already from the nature somewhere from the camera has been applied by convolving with the image, and there is some noise added. So this is the general model that the image that I'm receiving. Okay, it can be both or it can be one of them. But in frequency domain, because it's a convolution, in frequency domain I can write it in a multiplicative way. Okay, but for this set of slide, I'm mainly focused on noise itself only. Okay, so let's say I have just noise, added noise. So the original image will look like this. Now I have to find what are the characteristics of that noise, and based on that characteristics, I will find which filter I can use. Okay, so But for me, what is important? What parameters define the special character of noise? I have to find what parameters. Okay. Then is the noise correlated with the image or not? Okay. I can also look into the frequency spectrum and see that what is the Fourier spectrum of the noise. Okay. If it is a constant flat, it means that noise is white noise because it has all the frequencies. Okay. More plus. Okay. Sometimes the noise is also periodic noise. So what is periodic noise? It's repeating after some time. Okay. So you see that the noise here when we are adding, we assume that noise samples are independent of the special coordinate, and that is uncorrelated with respect to the image itself. I take noise samples, they're not correlated. This is the first assumption when I'm doing this type of filters, except for periodic. Periodic is there. If I don't have this assumption, I cannot find any filter. This is the first assumption. The second assumption is that the noise is independent of the image or signal itself. What do you mean by this? Like it's a completely different phenomenon. Two different things that I'll be adding. It's like independent of them. If it is correlated, then I cannot remove it. Because the signal and the noise. Yes, okay. So these two assumptions, whenever you are reducing the noise, these two assumptions should be good.
Maybe I see that these small dots looks like coming from the picture. So this is correlated.
It's not correlated. Correlation means that let's say here we have yellow and here some brown. So based on the color, the noise has some relation on that intensity. So if more intensity, let's say you have more noise, less. So there's some correlation among that. So
let's put correlation with this. See that.
Yes. If you plot the correlation for the noise, random noise, that is non-periodic. You will see it in that time. Okay. So you can plot it. And this is what we will talk about. Okay. Now, as I mentioned, there are different types of noise. So the one characteristics that we have to look into the for processing is the probability distribution function, which previously we called it histogram. Okay. So I have to see the probability distribution function of the noise, and once I have that, I can decide my. Okay. So what are the type of PDFs that we have? Yes. Normal is Gaussian. Yes, we have a constant or uniform. Okay. Then we have exponential. Yes, that's it. Poisson. Okay. What else? Gamma. Okay, or relay. Okay. So all these distributions of noise. The noise can have so many distributions, and based on that distribution, I will decide that what my filter will look like. Okay. So all these are the except sorted bit, it will not have a specific distribution. It is behave different. Okay. And similarly, you can have some other noises or mixed noise means that it has two types of noise. Okay. So what I will do, let's say I have a noise sample available. So how to find that which class it belongs to? Yeah. So how to make the PDF? Yes. So we just plot the histogram, and I have to see the histogram and see. Let's say if it is Gaussian shaped histogram, I say okay, this is a so it's a kind of curve fitting. Okay, not necessarily exactly the same. It will be a kind of a curve fitting. It will look like a Gaussian, it's a Gaussian noise. If it look like relay or gamma or exponential or uniform, and every of all of this noise has a specific distribution. Okay, histogram. Plus it has some we call it mean and variance. So if I know the shape, I mean whatever shape it is, plus I know the mean and variance, I'm okay, and I can design my filter different. Okay. So what is mean? I think we define the mean. And we define the variance already. Okay, so make sure that here we have the continuous because the noise is not quantized. Then it's not right? It's not quantized. It's a continuous property quantity, right? So starting with the very basic, we have the Gaussian noise. We already know that this is a Gaussian shape. So what I do, I take my noise samples, okay, and plot it in a histogram in the MATLAB or Python. We have a histogram function. Plot it if it's like this, it means that it's a Gaussian noise, and I can find the mean and variance of this. Okay, so this is Gaussian. Then we can have a relay is this type of thing. So what you will do, you are basically doing a curve fit, plotting histogram and trying to find out which of this distribution is closely matched to your noise. Okay. Okay. So this has distribution has this mathematical model, and definitely we don't need to go into these details. But what we want to know is the what type of distribution it is. It has mean this and variance this. Okay. Similarly, we have gamma distribution of the noise with this probability PDF and this noise, this mean and variance. Okay. Then we have exponential, and also we have the uniform. And one other thing, and also the examples are also shown. Let's say that this noise occurs in electronic circuit and sensitive to poor illumination and or high temperature of the sensors. The sensor temperature increases, the pictures or the signal is captured is not accurate. Similarly, this noise is present in range images. What is range images? Is let's say if I'm using a drone to capture the image of something from the top, I need to find how much is the height of the tree, for example. Okay, okay, so that is the range. You are finding the depth of the tree. So that is the range. Okay. Again, gamma is again occurs due to the illumination problem. Also, laser imaging. Like for example, you go to the eye doctor, you scan your eye, so it's using the lasers. Okay, to see. So this type of noise occur in that. Similarly, it's also this is also is present in laser imaging, also due to illumination problems. Okay, or light problems. Okay, and then we have a uniform noise. Uniform noise actually it's very rare in a real images, but in let's say if you are it occurs in the like synthetic images, like you are generating using the some MATLAB synthetic data or simulated artificial generated images, it can be common because it's very systematic. It's very evenly distributed, so this cannot be in a real case. Be in some simulated case. Okay. And now with the mean, this variances and PDF. Okay. And now one of the mostly famous noise in the image processing, one is Gaussian. If you talk about the random noise, that's Gaussian. The other is sorted paper noise. Okay. Sorted paper noise, what happens is that some of the pixel either it goes to low, some goes to high, low and high and low. Okay. Fine. So some goes to 255, for example, some goes to 0. Okay. So now let's say here I will just discuss it a bit in detail because it's simple, and also this is the thing that we don't discuss in specific processes. Okay. So let's say I have the probability that the pixel goes to high level, okay, as PS. Okay, PS the probability for the pixel, any pixel Z to go to the highest level, which is 2k minus 1. KR, K is the number of bits. Okay, and the PP is the probability that the pixels go to 0. So what are the probabilities of other pixel 1 minus this plus this? Okay, so it means that in the image, these are the number of pixels that are unchanged, same. These are the number of pixels that has 0 values, and these are the number of pixels that has high values. Okay. No. Either high, either low. No, why? No, actually, because this affects because some of the bits. Let's say this mostly this noise affects due to a memory problem. That is, the memory, some of the bits are missing. Okay, or high or low. Okay, okay. Now C is the value of any pixel. Intensity. So how to generate this type of noise? I will assign 0 to all location in the image where 0 appears in noise domain. And I will assign a value of the height to all the location in the image that has the maximum value in noise domain and leave the other unchanged. Okay, so some of the pixels according to this distribution will be assigned low or high. Also, the answer is also called bipolar impulse noise. Bipolar means because you have to either 0 or 1, right? Solid paper. That's why called bipolar impulse. Or unipolar is either PS or PP0, which means that either the salt is present or the paper is present. Okay. Also, it's called a data dropout noise, binary noise, short noise, spike noise. All are these items. Okay. So again, this occurs due to a sensor and a memory problem. Okay. So if you have memory, some bits are missing, some bits are not good. In the sensor, some sensors are not working. So this occurs because of that. Okay. So what is the total noise probability? It will be of course PS by PV. Okay. Probability of salt and probability. Okay, so let's, for example, if the probability of the salt is 0.02 and probability of paper is 0.01. So what will be the total probability? It will be 0.03. What it means that 2% of the pixel in the image are captured by the salt noise, 1% captured by the paper noise, and 3% overall are captured by salt and paper. Okay, so how to calculate the mean and variance here? 0 has the probability of PV, so 0 multiplied by this probability plus V is any other pixel multiplied with the other probability and then plus the high probability with PS. So this is the calculation for the mean, right? Yes or no? We just calculate the mean, each value is the probability. Okay. Okay, fine. So I think this is not difficult. Then we have Poisson noise. This is again an example. We have PDF this, mean this way. The good thing about Poisson is the mean and variance is same, and based on the lambda value, you can have different curves. Now, this Poisson noise is actually present mostly in the low dose CT scans. High dose is half of the body. So now what they are doing is that they are giving the low dose and trying to improve the image. So instead of a high dose, which will give a good image, we give a low dose, but after that we do image processing. Fine. But however, when you give the low dose, this type of noise occurs, which is Poisson plus Gaussian distribution, a mixed type of noise occurs. Now, it's our responsibility to process it. Fine. Okay, so let's say I have this image. I will plot the histogram of these and we'll try to find out which type of noise is present. So let's say I have this image and I plot the histogram. How it will look like? Agree or no? We have a black. Okay, we have gray and we have white. Okay, but if the same image, if I add noise, which is noise, what I'll get this one with noise. So if I add noise to this 0 location, it will go around 0 location. So there are 0 plus minus some values, okay, based on the mean of the noise. Okay, so I will get this curve. Similarly for this one, I get this. For this, I get. So this is if I try to map that which distribution this is close to the Gaussian distribution. Similarly for the related and others. Okay, so this is one of the way to basically find out. I did not separate the noise and image, but I'm just plotting. But this is very simple, of course. So I'm just coming to that point as well. Correlation means that the noise value depends on the value of pixel. Okay, one of the ways, let's say if you have a black, okay, you get Gaussian. If you have this gray, you get another type of noise, not the same. So it means the noise nature now is correlated to the color. This is one of the examples. Similarly, I can say that the noise amplitude varies with the amplitude of the pixel. So this can be another. So correlation can be in this form, but here no. Okay. So similarly here we also have some examples. The same thing with different noise. We have salt and pepper and other stuff. Okay. So another noise which behaves a bit differently and that is correlated among itself is the periodic noise, which is sometimes sinusoidal. We have seen this thing, right? If this is sinusoidal in the frequency domain, I will get 2 impulses at that position where we have that frequency. And how to remove that in the frequency domain? I can just filter out these 2. Okay, using these, which filter will help? This filter, which filter? No, median is for the salt and pepper. This for periodic. Which type of filter will help? Band reject will help. Yes, it will help, but what is the best one? Not filter. Okay, because band will already reject this thing. So already the picture, as I told you, that the picture is already low pass. So if I just reject this band, so everything will be rejected. Okay? Although you can have, you can still have. Let's say if you do band reject, what will happen? So if you do band reject, you have to do very carefully, like to cross the. Okay, but if you do the notch, it will just remove these 2 dots. Okay, but if you do the band reject, it will reject the whole band, this band, which may not be very efficient. Now the question is how to estimate that what type of noise we have. Okay, so there are several ways. One is I can transform the image to the frequency domain, and I see that what type of noise is present. I know already that the image itself it has a low frequency component. So let's say I get a very flat spectrum. It means that the noise is what? Flat spectrum. Flat spectrum is what? So what is that? White noise. So it means that noise is white. Fourier spectrum will give us some information. Let's say I get some spikes in the frequency domain. It means that it has a periodic, right? Spikes in the spikes. Okay, so spikes in Fourier means it's a periodic noise. So one way is to transform my image into the Fourier. The other is that I know that the sensor has some properties already. Okay, if I'm like going to finding this one, I can do that. Or the estimate from the image accordance. Okay, this I will come back. And if these 2 are not there, then what we can do is if it is possible, so I will take a flat image. Flat images means that it's like a constant intensity grayscale image. Okay, so I put a board in front of the camera, or I take a picture and I know that the background is gray, so I can subtract gray to get the noise only, and then I can plot this histogram of noise that will give me this. Okay. So now,
If you have like a ground truth.
yeah, you have the ground. Yes. If you know the actual. Okay. So one is this. Even if that is not possible, then the other way is I have in my image I have to find any area which has a constant intensity, take that one and plot the histogram of that, and try to match which area we have. Get my point? No. For example, here in this image, I take this part. I plot the histogram. Mean might not be exact same, but I can still estimate that this is a kind of a gray level. So it has, let's say, 150 or something, 200. Sorry, so 200. So I can subtract 200 get the exact mean, and this is look like a Gaussian, right? So you see how it can be from the image? This is not a noise estimation. Okay. So after the noise estimation, I can estimate mean and variance. Okay, and try to find out that what type of noise we have. Okay. So for the salt and paper, we also need the probability of salt and probability of paper, which we can count again using the constant intensity. I take this, so I assume that in one area, if I count the number of salt and paper and divide by the total number, I get the probability of that. So I assume that if that has number, it will distribute it equally among them. Okay, so this way I can estimate all the parameters from this model. So there are two types of now filters. One consider that the filter is same for all the image, which does not distinguish among this part that don't have noise and the part that have noise. But there are some other filters that automatically detect that which pixel has a noise, which pixel don't have. So fine, some of the filters we already did, so I will go very quickly and it's very easy as well. So we did deep filters, but now I will just discuss some others. Similarly, we define here, except these two and these two. Okay, so I will try my best to just go quickly over it. So one is the arithmetic mean filter, right, which we already discussed. So what we are doing is take the box, okay, take the kernel, and divide by the total number, take the mean, and which gives the mean, right? So which type of noise can be removed by this filter? Gaussian, random noise, any random noise. Okay, but as I mentioned, that Gaussian noise is the famous noise. So when I say Gaussian, any random noise can be really exponential. Okay, so any random noise comes under this. Okay, so the Gaussian noise is the better reduced by the mean filter. But again, as you are saying, your question, if I apply this, it will smooth the edges as well. So it, like make it blurry. Okay, so I have to somehow compromise between the quality and the reduction of noise. Based on this, also I have a geometric mean. Okay, so what this arithmetic mean is a mean when I add the numbers, the center of the addition of the numbers. But if I multiply, geometric mean is the mean of multiplication. If I multiply them, the center point of that will give me the geometric mean. Again, geometric mean filter is just, if I take the box here, I was adding it, right? Adding and dividing. So this was the conclusion. But if I do this, I am taking the filter of the kernel and I am multiplying all the pixel inside and the power. Okay, one by size of that. So this is geometric mean. Okay, this is nothing new. Huh? Geometric mean, harmonic, all these are actually the sums that we use in mathematics. Yeah, yeah, in the statistics, right? So if I do this, I can have reduction in Gaussian noise, but this is not effective in paper noise, and it loses less. This is the problem. If I apply this one, it will smooth the image, so I will lose the add information. So if I use a geometric, I will get rid of this, but also I lose less information as compared to mean filter, because here it smooths everything. Here you will lose the detail, but less as compared to this. Okay. So now why is it ineffective in case of paper noise? I know that this is not good for salt and paper in general, because this is everything, but effectively or specifically, paper noise is like totally ineffective. Because what is paper noise? It makes it zero. If the pixel is zero, what I will get here? What I will get? Zero. Yes. And then total term, because the multiplication, everything becomes zero. So that's the problem. That's why the paper is ineffective. Not only that, it will make the things even more, because it will make the whole box equal to zero. Okay. Then we have harmonic mean. Harmonic mean is the mean. It's actually the, like, this is the mean of when I sum the number. This is the mean when I multiply the number. This is the mean when I do the rate of change. Okay, like per pixel summation. When I do the per pixel summation, I get this. Okay, so again, this is a kind of a mean. So this is works well for the salt noise, also Gaussian noise, but fails for paper noise. Why it fails for paper noise? Again, if the pixel becomes zero, this becomes infinity, and this whole becomes zero. So ineffective for the paper noise. But salt somehow works. Okay, fine. Okay, so then we have another filter which we call it the Contra-Harmonic mean filter, and this is a combination of these terms. From these terms, I can either make this filter or this filter. Okay, how? We have Q here. If you see Q, so if the Q is zero here, above it 1, below will be.
So to is zero.
One. It will be 1, and then sum up becomes NN. Right? So it will become a mean filter. If Q is minus 1, what it will look like? Harmonic. Okay. And if so now this filter, yes, this filter is a kind of filter I can make either the mean or the harmonic mean. Now the other thing is, if Q is positive number, this filter will help in estimating or eliminating paper noise. Okay. If the Q is negative, it helps in eliminating the salt noise. Why? From the expression, just tell me why. Well, read this one. Positive Q eliminates paper noise. Here. And if Q is negative, it eliminates salt noise. Okay, let's say if you have negative, what will happen? It will act like a harmonic filter, right? And if it act like a harmonic filter like this, it helps in reducing the salt noise. Okay, so for negative numbers, it will be salt noise. Okay, so the opposite to that will be, yeah, so if the positive we have, it will help in reducing the paper noise, but it will not help both together. If both are there, it will not help. Okay, is this clear?
What about if we do it one by one?
No, it still will not help, because if we reduce one, the other will enhance because of the expression. Okay, I'll show you. If we
use one by one,
it will not help. Okay, so let's see some images. This is simple image. We added the Gaussian noise. I think this is the mean, simple mean, arithmetic mean. This is geometric mean. Okay, and you can see that geometric mean somehow is better than the arithmetic mean if you see this areas. Okay, so it's somehow better, but definitely if you use some quantitative analysis, it will be better explained. Let's say you have a paper noise here and a salt noise here. What I have to use? Which filter I have to use? contra-harmonic. Okay, contra-harmonic for the paper should have q greater than 1. Okay, so if this is positive, q positive, this eliminates the paper, and if q is negative, this eliminates the sort. Let's say if I do the opposite, so what will happen? Okay, it even enhanced it. Okay, so fine, and then we have some. Okay, yes, we have some filters. We call it order-statistic filters, and we have seen that, right? We have made a filter. We already saw that we have min and max filter that takes the min or max, and these two filters are good for sorted paper. Max is good for paper noise, so the paper has 0 values. It will enhance it. Min is good for sort. Okay, and we can have this expression as well. Then we have also midpoint filter. Midpoint filter is taking the max in the area plus min in that area divided by 2. So it's like giving some midpoint. This is again good for Gaussian noise or uniform noise. Okay, because it's a kind of a mean type of thing. Okay, not exactly mean, but it's. Then you have another filter which is called alpha trim filter, and this filter is good for Gaussian and sorted paper both together. Why? It's a mean filter, like the mean filter we have. So what we are doing, we take a area, okay, and take the mean in that area. Okay, but however, I just remove some of the points, the low intensity points in that area, high intensity points based on the D. Let's say D is 2, so I remove 1 point from the beginning and 1 point from the end. See what I'm saying? Okay, so I take the box, inside the box, I sort it, intensity levels, take the minimum and maximum out, and take the average of rest. So what will happen? Why am I doing this? Okay, so I have now the two properties. One, I'm taking the mean to reduce the random noise, and I'm removing the max and min because of the sorted paper. Okay, so in this way, it's serving the both purposes. Okay.
So this one looked like different. I remember what we did there. There was different.
Yeah, we have max min we discussed, and we also discussed the median, but we did not discuss these two. And this is what I start what I said. That last one from the filter point, and this is from the image sample. Okay, so image, I have mine. So which filter I will select, and there was the filter how to apply on image. Okay, so this is the main. Okay, so now here what we have. Okay, we have salt and paper noise again, and there is another way. We have the median filter, but let's pass through the median filter several times, like I checked here. So this is salt and paper noise. I apply the median filter. Again, on that I apply the median filter, and again I apply the median filter. So you see that what is happening is, you see here there are some points that are still there. See them? Here it's been reduced, but still we have one here, right? One and maybe some other this one. But here even it's reduced. But again, the question is how much time? Okay, because if I keep on doing this, I may have lost the information. So I have to make sure that I should not overdo it, like overfitting in the neural network, or underdo it. Okay. So one way is to take after every pass, I take that image and yeah, visually you can do that, but sometimes visual information is not really good. So mathematically, what it should be. How I will find it. So what I will do, for every pass, I will take that image or find the error between that image and the previous pass image. Okay, so if I find the error between them, if the error becomes constant or very small, I see that nothing is improving. Don't do anything. Yes. Okay, so this is one of the ways. Can be other ways as well. Overfitting and overfitting means that you are overdoing it, like you will start using the image information.
Subtraction always will give me somebody.
Yes. So if I plot the passes versus the error, error is what? Error is the this pass image minus the previous one. Okay. It can be mean square error. Normally we do mean square error. Okay, but for simplicity I just know. So the error will start to what? Decrease, and either it will stay the same or it will start to increase. Why it will start to increase? Overfitting, because I'm using that information of this. So I can pick that point and I can this is a
this point is a subtraction will not come. The subtraction for if we practice will give me some value.
Yes.
So I'm just plotting it. The metric for me to define and I solve this point. So what is the metric? The metric to tell me this is the point, this is the best one.
So I have to plot. I plot these two and find the minimum.
But how can I plot this here?
Two images. Like for example here, this is the one, right? So yeah. So now this is okay. So what I do? This is the first part, right? This is the second one. So the second one I subtract these two. Then third one again I subtract these two, and I'm plotting it here. This is the first part. This is the second. So it will decrease because of the noise. Noise, right? But after that it will start increasing. Why it will start increasing? Yeah, gray image. It will start losing the information of the image itself, because now the filter is saying that okay, it's the noise. Image itself information, it's considered the noise.
Yes. We have some 3 by 3 linear filter. This equivalent to one time. If you have a 3 by 3 linear filter, then that's 3 or 4 times sequentially. So this equivalent to 1 by 9. So
the video is not linear. It is not linear. Let's say that is for the linear.